All right, graph the piecewise function. What does that mean? It means it is a Frankenstein function. It is a single function that has multiple functions sewn together. The arm of an owl, the body of a cougar, and the other arm of a fish. I don't know. It's a Frankenstein. It's got crazy things mixed together. But what do we know? We know that the function is simply x squared. Y equals x squared. Your friend, a parabola, given the condition that the x values are less than equal to negative 1. So think about what that means. Imagine we were to graph a normal parabola like that. Imagine parabola land says boom, origin, boom, negative 1, 1, boom, negative 2, positive 4, like that, right? That's our friend, the parabola. That's at least a left half of the parabola x squared. But look, we have this condition, x is less than negative 1. So what that's saying is we only want to see this graph when the x value is less than negative 1. So I need to erase all of that. Or rather, I shouldn't even have drawn it. But there we go. Here's the x value of negative 1, where the y value is 1. And that's my graph. To the left, it's just a parabola. To the right, it doesn't exist as a parabola because we need to look at the next condition. But that's that. Notice that x is less than negative 1, so I've used an open circle on the graph to indicate such. Now, next condition, right there. This function will look like the graph of y equals 2x. Let's do a different color. Y equals 2. That's still pretty dark. Let's maybe get dramatic with it and use pink. Y equals 2x when x is between negative 1 and positive 1. So let's go positive 1 right there. Let's maybe do some tick marks to help us be a little bit more accurate. But y equals 2x. It's a linear function. The slope is 2. The y-intercept is 0. So I know I'm going to have a point right there. My slope is 2, so if I go left 1, I have to go down 1. I know I have a point right there. If I go right 1, I have to go up 2. I said left 1, down 1. I meant to say left 1, down 2. So I drew it, I didn't say it. But look, we have that graph right there. It's a linear function. It is simply linear between there. So there's our pink graph. X squared was our black graph right there. And let's do the last piece of this piecewise function. Let's do it in purple. Let's do negative x plus 6. And we're doing this only when x values are greater than or equal to negative 1. So I actually now realize that I goofed up that last bit. That right there, notice that our function y equals 2x was only defined when x was less than 1, not at 1, so that has to be an open circle right there. Okay, do you see that? I hope you do. Okay, so when x is greater than or equal to 1, I'm the function negative x plus 6. So y equals negative x plus 6 when x is greater than or equal to 1. So what's our starting y value? Well, plug in the x value of 1. So negative x value is 1 plus 6 gives me 5. So this graph has to start up at 5. So 1, 2, 3, 4. Let's put 5 up there. There my graph starts. It is a filled in circle because of the greater than or equal to right there. And the graph has a negative slope of 1. So I know that if I go over 1, I'm down 1. If I go over 2, I'm down 2. And it continues like that forever. So let's now use this Frankenstein function to graph some stuff. What is f of 1? Well, f of 1 says go to the x value of 1, tell me the y value. Well, here's the x value of 1. What's the y value? It's that spot right there where we have the filled in circle, which has a y value of 5. What is f of negative 1? Well, that says a very similar thing. It says go to the x value of negative 1 and tell me what's the y value. Well, that's my y value right there where the circle is filled in solid. And I get negative 2. And then finally, on what interval is f of x greater than 0? That is just asking you, hey, tell me the x values where this function is positive. Well, notice that we're just a positive parabola, like all the way over here, all negative x values, until I hit that open circle, because at that point I jump down. So if we're studying the intervals where x is positive, we are starting all the way from negative infinity, because that graph goes on forever. That's what the arrow means. And it's going to continue up until we hit this open circle right here, which happens at the x value of -1. So I'm positive up until -1, but then notice that -1, I hit that value right there. We already said that -1 had a value of -2, which is negative, therefore not positive. So I stop being positive at -1. But when do I start being positive again? Well, I start being positive again right after this 0, which has an x value of 0. So I will union this with the set of numbers starting at 0 and continuing how long? Well, look, positive, 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 open circle, but the value there is still positive. Positive, 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 up to a certain point. When do I stop being positive? That's actually not super obvious, but we do know that this graph right here is represented by the function y equals -x plus 6. And we could ask the question, when is this function, -x plus 6, positive? Well, when is it greater than 0? We want to know, when is this function, -x plus 6, greater than 0? And let's just do a little algebra. Let's subtract 6. We get -6 is less than -x. So multiply by -1. And we get a positive 6, and we get a positive x, and we multiply by a negative. So we switch that sign. So x has to be less than 6. If x is less than 6, then we have a positive number. So that will remain positive up until the x value of 6. At 6, it's a 0, and we disclude that number. So those are my positive intervals, and we done crushed this problem.